Okay, so the two options for you, one of them is Monte Carlo, and the other one is temporal difference learning. So Monte Carlo says you're at the state S, you just run everything, you figure out what the value will be just based on the simulation you ran. So imagine it's like you're playing the final project game, and you just roll the dice, you play out the rest of the game, you see did we win or not. It's either 1 or 0, right? That's the Monte Carlo. Temporal difference learning says you don't need to play out the whole game. Just take the value, v hat, take the value of what you think the next state will be. So you just play one turn of the dice game, you roll the dice once, you see what the value is at that new state, and then you update according to that. And the question is, which of these two options is unbiased? I'll remind you, what does unbiased mean? Unbiased. So we've talked about this once or twice already. Unbiased just means that the expected value, right, the expected value of the update, u, whatever we use, so u is either a sample return, that's Monte Carlo, or u could be r plus gamma v hat of s. W, this is the temporal difference learning, TD learning. And this is what the value function v thinks one state in the future is worth. What v thinks the value is. Okay, so those are the two options. And unbiased means the expected value of u given our current state, given the current state, that should be, on average, it should be the true value function v pi of s. So is it true that the expected value, like the u we're using is a bit random, it's random for the sample return because you played the whole game at random, and it's random in, so this should have a prime, just importantly that I didn't write it here. TD learning is you go one step into the future. Taking one step is also random. So one of them is random because it has the whole history of all the possible moves in the game that will happen. The other one is random because you have one step. And unbiased means it should, on average, be equal to the true value function. The true value function. Okay, and it's split 3 to 5, which is close enough to 50-50 that I'm going to make you guys revote. So 3 to 5 is not a consensus. So let's take the vote one more time. Talk to your neighbors about which of these two options you think is more likely to be unbiased. Okay, so we're up to 7 responses. What do people think? Okay, it's still split. It's still split. Okay, so let's talk. Who wants to defend their side? Somebody who voted for one or the other. Yeah.
So I picked temporal difference update because if you take the expected value, that's going to be equal to the value function at best.
Okay. So it's true if you do the expected value of the temporal difference learning thing. So if we actually sit down and do some calculation, then you would get the expected value, the expected value of v hat s prime w, right? So you would get the expected value of what our value function thinks. And this is certainly the expected value of some value function. The Bellman equation for v pi, we know that v pi satisfies, it's the expected value of v pi of s prime. Okay. You know what? Let me put in the actual little extra things because then it'll be perfectly right. So for the temporal difference learning, the expected value of u is equal to the expected value of r plus gamma times this stuff, and we know the Bellman equation says that v pi of any state s is equal to the expected value of r plus gamma times v pi of s prime. So they are very similar. So for temporal difference learning, you get this as the expected value, and for the true answer, it's this. So you might think, maybe, They are the same. Okay, that's the argument for why temporal difference learning might be the answer. Does anyone have an argument for why Monte Carlo would be the answer? So these look similar. So this is the argument for temporal difference learning. The equations look similar. Okay. That's the temporal difference learning argument. Who voted for Monte Carlo? Does anyone want to tell me why they voted for Monte Carlo? Are we scared the Monte Carlo people away? Rocky, I think you said you voted for Monte Carlo. Is this accurate? Do you want to tell us why? Rocky, this is his first class today, so.
I have no idea what's going on.
So you guys already know what's going on, but you voted for Monte Carlo. Why did you vote? Maybe you were just guessing. But maybe you have a reason?
Reason comes from experience with Bayesian inference, where Monte Carlo you tend to not introduce bias.
Okay. So Rocky, because it's his first day, doesn't know about the equation. He doesn't know about the Bellman equation, but he knows the definition. He only knows the definition. So what is the definition of V pi of s? V pi of s is you start at s, and it's the long run expected value. That's what it is. So the definition of V pi of s is it's the expected value. What is it the expected value of? It's the expected value of your long-term reward. Right? That's the definition of the value. Now you start at some state s. You have some random trajectory of things that can happen to you, and the average of all those random trajectories, the expected value. So you could write it as G0, the expected value of the total return you get starting at 0, or you could write it as the reward you get now plus gamma times the reward one step in the future. It's any of those. So this is the definition even before the Bellman equation, and this right here is exactly the Monte Carlo update. So almost by definition, the Monte Carlo update is unbiased. So the correct answer is the Monte Carlo update. How do I reveal the answer? I have to click display. Yeah, there we go. So the Monte Carlo update is correct, and it's almost by definition. And it's very tempting to think that the temporal difference learning one is right, but there's this difference in that the temporal difference learning one is learning. It knows about v hat. It knows about our approximation, and it doesn't know about the future, or it doesn't know about the real value. So the temporal difference learning one can be biased. And in fact, so the name people give to this type of method, because the temporal difference learning method is learning in terms of itself. So v hat of s is given in terms of v hat of s prime, right? You're learning about a current state based on what happens in the future, based on one step into the future. This is called a bootstrapping method. Bootstrapping. So bootstrapping comes from this like joke term, which is pulling yourself up by your bootstraps. Bootstraps are these little tabs. So you try to pull yourself up, you go like this, you pull really hard. You don't go anywhere, right? You can't pull yourself up by your bootstraps. And that's exactly what we're doing here, right? We don't know the actual answer. We have no idea what the answer is. And we try to learn a little bit from our non-answer, and we try to import that into our answer, right? So it's kind of like a joke, like this shouldn't work. That V is learning in terms of V. So we could have had this discussion when we first learned about temporal difference learning. I think it was more plausible then. Now we're doing all this stuff with gradient descent and everything. So this question of how does this thing actually work is still sort of up in the air. And we're going to see today that under bad circumstances, if you choose the function V kind of incorrectly, it can really spiral out of control and it really doesn't work. But there are some cases where you can make sure that it works. And in what we did before, when we did everything with a big table of values, where we just kept track of every possible state, that stuff is okay. So what we did all in the past was fine. We're going to see today that sometimes bootstrapping goes wrong. Let me draw you the picture of why there is hope, where you shouldn't think bootstrapping is completely terrible. And I'm going to use the analogy of our final project and what we've been doing of games. And games sort of you can kind of think of a game as all the states in a game. Imagine these are all the states in a game that are little nodes and they're connected by edges. So all the states are here. And as the game goes on, you can kind of make a general picture of a graph from the beginning of the game to the end of the game. So the beginning beginning of the game to the end of the game. And like very roughly speaking, there's sort of a time dimension that as time goes on in the game, you get closer to these like end game states. And it's not true for every game, right? Like sometimes there's a game where it'll go backwards, it'll get closer to the beginning. But for example, in our final project, the end of the game is there are few squares remaining, right? The players are moving forward, and the number of squares they have until they reach the end of the column, that's always going down. So the end of the game states are few squares remaining. Few squares remaining. And the beginning of the game states have many squares remaining. And so the reason it's hopeful that temporal difference learning might work is that it's not completely unbiased, but for sure it is unbiased near the end of the game states. So for example, if you actually look at a state and a player has claimed the number of columns needed to win, you know for sure it's a win. So you know for sure the value function near the end of the game states. And the way your temporal difference learning works is it's sort of picking two states and it's learning, it learns about this state, it learns this, learns about this state, using this state, using this. So it's kind of taking information from the future and dumping it into the past. And if we're unbiased at the end of the game, if we know the right values at the end of the game, then over time, as our algorithm runs, the space of places where we're unbiased is going to slowly, gradually move backwards in time. So after you've run the algorithm many times, maybe these ones are all unbiased, right? And then you run it even more, and now these ones are all unbiased. So it's true, maybe you have some garbage information over here, near the beginning of the game, especially when you first start running the algorithm. But over time, you sort of hope that this flow of information flows from the states that you know, and then you're slowly getting better and better, and the information is moving backwards. And by the time you finish running it, you hope that you've learned the value of all the states. So that's the hope, and it does work well in situations like this. We're going to see that there are some, in gradient descent, there are some pitfalls, but that's the general idea in bootstrapping, and you can hope that it works as long as you have kind of a starting point to work on. So it's not really like the situation I showed you, pulling up on my boots. It's like I'm pulling up on something, and then something pulls on that, and then something pulls on that, and something pulls on that. So we do kind of have this anchor state, right? This is the anchor of the end of the game states. We know the value there because we know the rules of the game, and we hope that temporal difference learning will take the information and pull it back in time all the way to the beginning of the game. I guess this is also why it's called temporal difference learning, right? So you're learning about the future, you're using the future to learn about now, and hopefully, because of this kind of picture, you have a more accurate idea of what's going on in the future than now, and so you can actually learn something from the difference. Okay. Any questions or comments about that? So this is like an important part of this temporal difference learning. I think you guys all voted for temporal difference learning because I've been saying it's really good. So it's true, it's really good, but it's not unbiased. So it's good in other ways. Well, maybe do you guys know some of the other ways it's good? So temporal difference learning could be biased. Yeah?
You don't need to play out the whole game.
Yeah, exactly. So it's more efficient with the samples, right? You don't need to wait until the end to learn. So it's more sample efficient. It kind of has lower variance, because you can imagine that in a situation where I want to see the value of this state, if I play a long time into the future, maybe I get unlucky sometime 100 steps from now, and then I get the wrong I get something far from the average now because I got unlucky in the future. Whereas if you only take one step now, there's sort of less chances for you to get unlucky. We saw that with Alice and Bob playing soccer, right? So Alice passed it to Bob, and then Bob normally scores about half the time, but Alice got unlucky because the one time she passed it to Bob, Bob didn't score, and so like Monte Carlo says Alice sucks, but temporal difference learning says, Alice is doing the best she can. Okay. So, temporal difference learning is good, but it's not unbiased. And what I said before about stochastic gradient descent, some purists will say it's only true that it's stochastic gradient descent if it's an unbiased thing. So if you're trying to find your way to the CN Tower and you're asking random people, that's only stochastic gradient descent if the people on average point you to the CN Tower. If the people on average point you somewhere else, then of course you're going to have a bad time. You're going to get stuck somewhere else. Okay. So, and this is from the textbook. So if the thing is unbiased, if it's unbiased, then there are theoretical guarantees that you converge to some local optimum. And if it's not unbiased, then you have to do something else. And we're going to see that in general, this update can go completely wrong if you do a bootstrapping method plus some other things. And that's what we're going to see sort of today. And before I show you the bad stuff, I'm going to show you the good stuff. And the good stuff happens when you do things as simple as possible. When things are simple, you can make sure that things are fine. And when they're simple, you can have some mathematical argument that works. Whereas for a general function v hat, there is no guarantee at all that this update rule is going to work. So that's what we're going to do today. We're going to start with the most simple thing. We're going to look at that case. And I actually think that the most simple thing is mostly what you're going to use for your projects, maybe with a little bell, some little bells and whistles put on, but it's better to start simple. So the most important question is, what is the simplest? So yeah, by the way, these are the two algorithms from the book. I think last time I showed them from the slides from David Silver's course, but these are from the textbook if you want to check them out. In the textbook, they call the method a semi-gradient. They call it a semi-gradient because when you do the gradient, you only do the gradient at the state S and not the gradient at the new state S prime. So it's sort of like we have these two states, the past and the future, and we're only using the gradient from the past. That's why it's called a semi-gradient. But this is exactly what we did last class and this morning on the first Mathematize. Okay, but this brings me to the important question for today's class. We want to do the simple thing. We want simple. Want simple. So v hat is the functions we're talking about. What is the simplest possible v hat? What is the simplest possible function? That's what we're going to start with. So now you guys have to tell me, what is the simplest possible function? What kind of function could we study first for v hat? So it's going to depend on the states and the weights. And someone says, come up with something we can do, right? Just like last class, I came up with this thing that was like linear on each of the things, and I had the slopes. What is a simple possible function you could do? Over here? Or you're just stretching? Okay.
Is it the equation of a line?
A line, okay. Equation of a line. A line, okay, that's one idea. Let's make a list of ideas. One, a line. What were you going to say, Jordan?
Just like all equal weightings.
All equal, what do you mean by all equal weightings?
Like the weighting vector, like.
Oh, like the w's should all be equal to each other. The big vector of w's should just be one number repeated?
Yeah.
Okay, so I think if you have one number repeated, that's kind of just like having one parameter, right?
Oh, okay.
Right, so I think you're thinking, you're thinking the right thing. I said the simplest possible function, and your idea is use less parameters. And that's totally true, right? The less parameters you use, the simpler the function is going to be. But at the end of the day, you have some number of parameters, and you got to put them in the v hat function somehow. And so I want to know is how do you put them in? Yeah. So it's a good idea. So it's simple. I guess I want the simplest form, right? The simplest form, not the actual simple. I guess another simple one is a constant, but we know that's not going to work, right? Okay, so a line is a great idea, and the line is the answer I was looking for. What does a line mean in this situation? So a line, this is why you guys took linear algebra class. What does a line mean in high dimensions? A line actually is a linear combination. So it's actually going to be a linear combination. Okay, so that's what we're going to do first, the simplest possible thing. And in this situation, the v hat function is going to be a linear combination of the weights. So we have this w, which are the weights, and the weights are a vector. And we're going to do, so w is actually like w1, w2, all the way up to w number of parameters. And the simplest possible thing you can do is make this equal to, let me fix this a little bit. So the simplest thing you can do is do a sum, I equals 1 to number of parameters of wi times something, right? We're saying the function v is going to do a linear combination of the weights w. And then the something doesn't depend on the w's anymore, right? Like if you put w times w, that's not linear anymore. So this something doesn't depend on w at all. And if it doesn't depend on w at all, it just depends on the state s. And so the most general linear function you can do is this kind of thing. So you have some function of the state s. And the function can depend on which parameter you're doing, right? You could have a different function for weight 1 and a different function for weight 2, and so on. And so the textbook calls these xi of s. So xi of s is a function, maybe let's write it like this. It is a function from the state space S to the real numbers. So it's like the ith function of the state space. And you do a linear combination of all these different functions, and that gives you some value function vi. So these are linear in W, and these x's, they have a really suggestive name. The x's are called features. Features. So for every state in your space, you can have this function that tells you how much of a certain feature is there. And this really simplifies things quite a bit. For one thing, the gradient is nice. So we know that during our update, you need to take the gradient. And that brings us to the next mathematized question, which is if you make a linear function like this, so we're testing not just your linear algebra today, but also your calculus. If you make a linear function like that, what is the gradient? What is the gradient? So we're gonna do this on mathematize. You guys take a second and think of the gradient. So we have this function that's a linear combination of the features, and I want you to do the gradient, because the gradient is an important part of the update rule we had. So take a second, write it down, think about what's going on in this situation. Okay, so we have 8 answers. Let's see how I would do it. So I'm going to take the derivative. The thing about gradients you got to watch out for is it's this like combination of vectors and derivatives, and you can easily like bamboozle yourself into mixing something up. And I think the easiest way, if you're stuck or don't know what to do, just do one of the components. So let's do the first component. The first component. Let's do the first component. Do that. And so that's the first component of the gradient. That means the first component, that is the W1 derivative, right? And now what I can do, now we're in Calculus 101 land, and it's not so bad. So what's the derivative with respect to W1 of this big sum, I equals 1 to n of Wi times the ith feature, xi of s. And what is the first derivative doing? Well, it's the derivative with respect to W1, so actually this whole thing, this whole big sum, you could write it as W1 times x1 of s, plus stuff we don't care about, stuff we care not for. Right? The other stuff is W2, W3, none of that matters when you do the W1 derivative. And so the question is really, what is the derivative? What is the W1 derivative of W1 times something? It's just the something. The constant multiple rule, if you want, plus 0. Or if you want 1 times x1 of s plus 0, which is x1 of s. So if you do the first component of the gradient, you get x1. If you do the second component, you're going to get x2, and so on. So let's see how many of you guys got that right. Okay, a little bit split. 4, okay, it's the majority answer, the most common answer at least. 4 people got it right. The vector whose ith entry is xi of s. And this vector is called the feature vector. So the gradient of W is exactly, of SW, is exactly this vector of x1 of s, x2 of s, x to the number of parameters you have of s. And this thing is called the feature vector. And this feature vector is like all we care about. If you know the feature vector, you know all the values of the x's, that's the only thing the function will see. And this is great for us because like we've talked about how the state space of a problem can be huge, but we can choose what the features are. So we can look at the game and say these are the relevant features that we think are going to happen, and we can encode those in our x's. So here's the slide from David Silver talking about the feature vector on the next thing on features. And so here's the feature vector. And the things you could put in your feature vector are, like if you're doing a robot, you could put one of the features could be how far away are you from your home base, right? So we've taken all the complexity of all the possible states you could be in, all the possible things that you could see, and we've reduced it down to one number. How far are you away from something? In chess or something, right? Chess has some huge astronomical number of states because a state means the pawn is exactly here and the other pawn is exactly here and the bishop is exactly there. But a nice feature would be like, have you castled yet, right? 1, if you haven't castled yet. 0, if you've already castled. Another feature could be, do you still have your queen, right? Like that's a nice feature that encodes something important about the game and really dramatically simplifies the complexity of the problem. So we're really hoping that by condensing down to this vector of features, you can say something about the problem without having to get into every possible state. That's the idea. And we've seen already, I just made you guys do it, that the gradient is actually just this feature vector. And that means the gradient descent rule becomes extremely simple. So this is on the next slide here. Here is the linear combination of features, right? Which you could write as a vector form. So if you want to do a bold x for the vector x, we're really doing the vector x times the vector w, the feature vector inner product with the weight vector. Okay, and now if we do gradient descent by using this square law subjective function like we did last time, the gradient descent rule becomes this. So before, the gradient descent rule at the end had the gradient, but the gradient is exactly just the feature vector. So now gradient descent is a very simple form. Maybe I'll write it one more time underneath. So the gradient descent rule before, or in general, is that w becomes w plus alpha times v pi of s, or whatever you're using as an estimate, minus v hat of sw times the gradient. And for linear functions, for linear things, w just becomes w plus alpha times v pi of s minus v hat of sw times the value of the feature vector. So the weights are getting updated by the features. And so there's this nice interpretation. This is why I really wanted to keep this slide from David Silver, which is that says the amount you update, right? How big, it's a product of three things. There's three terms. So the first term is the learning rate or the step size. That's the alpha, the step size. The next term is how badly off you were, right? Like you predicted v hat, and the actual answer is v pi. So the second term is like how big of an error did you make? That all makes sense. We've seen that before. But the new term is the feature value, and this is saying if a feature is really present and you made a big mistake, you got to change that a lot, right? If a feature is barely present and you made a mistake, well, don't change that feature a lot, right? So the amount you're changing things is proportional to how big the error is, and also how much of that feature is present. And so by changing things in this way, it's a very intuitive explanation of what's going on. You're updating things according to how much of the feature is present. You're updating according to how much of the feature is present and how big of an error you made. And so doing so, it makes kind of intuitive sense to me. Okay. And here is the other important thing from David Silver's slide, which is very nice, which is that unlike the general case where I said bootstrapping, we don't have a guarantee, it could go wrong. In the case of linear things, the stochastic gradient descent rule converges to some kind of global optimum. So if the things are linear, you will get convergence. So convergence is guaranteed if v hat is linear in the weights. So unlike the general case where maybe you kind of go in circles, as long as you're doing things linearly, things can't be too bad. Why is it that things can't be too bad? The proof is in the textbook. I'll do the special case in a second, and we'll talk about these. But I wanted to show you very briefly in the textbook, they have the proof. So if you're a theory person and you want to see some theory, you can see the proof of the convergence. And the proof really just becomes linear algebra. So you have some matrix, the update rule looks like this, and everything is linear. So there is just some matrix A that you're updating by. When you go to update the weights, on average, you update them by applying some matrix A. And then you can just take out your linear algebra textbook, look at the eigenvalues of A, and under certain conditions, you can prove that it has to converge, and then you just have to verify those conditions. So it really is like a fixed point theorem, like you're multiplying by matrix A over and over again, and that's going to bring you closer and closer to a fixed point. So if you're interested in the proof, I think this is totally readable, and it's like a nice connection between theory and what we're doing, because I know most of the class hasn't had a lot of theory. Okay. Let's do some special cases of this feature stuff. So I'm going to start with, actually, let me do this first. So this is another slide from David Silver where he is showing us the various convergence properties. So if you are doing Monte Carlo learning means no bootstrapping, like you have an unbiased sample. And if you're doing Monte Carlo learning, then you can do anything you want. So you can do a table, like we had for the first part of the course, where you just record the value of every possible state. You can do linear features, that will work, or you can do nonlinear features. Everything is unbiased, so things will converge eventually. The downside of Monte Carlo is it's kind of slow, right? You have to wait until the end. You don't have this immediate update. For temporal difference learning, in general, you're screwed. This is what I said this morning. In general, no guarantee. Could be bad. Okay, bad is in green for some reason. But as long as you're doing linear features, then things are good. And you're guaranteed to converge to something by linear algebra. So temporal difference learning with linear features somehow works better. This is all if you're trying to stay on policy. So you're trying to learn about the policy you're doing. We did talk briefly about off-policy learning. That's where you're trying to learn about a situation watching somebody else do it. And in that situation, things get more complicated. But so Monte Carlo will still work, and temporal difference learning can go awry in this situation. So the textbook calls this, they have a great name for this, they call this the deadly triad. The deadly triad. What is the deadly triad? It's not a gang or something. It's these three elements, all of which are kind of sketchy on their own. So there's bootstrapping, off-policy learning, and the third thing is a nonlinear functions. So bootstrapping is when you don't have an unbiased sample. You're kind of learning from what you already have. Off-policy learning is you're not even driving the car. You're just watching somebody else drive the car. And nonlinear functions are when you combine the weights W in some complicated way that's more complicated than linear. And these ingredients, sort of individually, each on their own, can be okay. Like if you have one of the deadly triad, it's not so bad. But if you have all three, you're definitely gonna be screwed. Or at least there's no guarantee that things will work. And in fact, the textbook has some nice examples of specific examples where things go crazy and spiral out of control. So if you run your algorithm, the weights will just get bigger and bigger and bigger, and then they'll explode to infinity. And you won't learn anything about the problem. Okay, so that being said, we're going to mostly stick to things that are close to linear. But at this point in the game, you guys are very close. We kind of know 99.9% of the stuff that you need for the final project. So the final project has you learning how to play a certain game. And basically what you're going to have to do is come up with features. You're going to design the features, and then you're going to make an algorithm that works using the features and is going to learn better and better weights. So next class, we're going to have like a big discussion, I think, on specifically the final project, going through the code, talking about exactly how it's going to work. But even this class, we can start to talk already, what are the features going to be in your final project? So this is really like the final project. A lot of it is going to be coming up with features. And we're going to do a little bit, how do you spell project these days? Project. One of the things you're going to have to do is come up with features. And then so the simplest possible thing you could do is just combine the features linearly, apply one of the methods from the class, and then you can apply little bells and whistles to it. You can make the features better or worse. You can try to train it faster or slower. But everything is going to be a variation on sort of this starting point. And so, the next mathematized question in our final project. What are some good possible features? So this is just, we're going to spend maybe 10 minutes just discussing this to get the ball rolling for next time. And next time, we're going to kind of go deep on different possible things you could do for the final project and sort of like, what is your strategy going to be to get things to work? But to start with, what are the features? like this from the textbook, from the section 9.5, feature construction from linear methods, that you could take a look at to try to get some ideas. Okay, tile coding, similar. What else do they have? Okay, so some things to look at for next time. Okay, but let's go back to our game, and this is going to sort of like just be the start of a longer discussion that we'll carry over next class. What are some possible good features for the final game? So remember, a feature is something that inputs the state space and outputs a number that just tells you how much of a certain thing is happening, right? So busting from a given state, like the probability to bust from a given state, that could be a feature, right? That's something that inputs the state and outputs a number. That's fantastic. So the computer maybe wants to know about what is this probability and then incorporate that into its final estimate for the value function. Advancements in each column. This is also fantastic. This is like the simplest thing, right? So in Can't Stop we have 11 columns. How far you are in each column, that's a feature. That's a number. You take the state space, you output a number. How far are you in the third column? Totally valid feature. Of course, it's going to be very important. I will say one thing. Remember, the features are getting combined linearly, right? So if you're going to use advancement in a column as a feature, that means that you are automatically saying that being twice as far is twice as good, in some sense. Is that what you really want? Is that true in the game? You have to think about it. Okay. The number of illegal columns, absolutely. That's something like that. Whose turn it is? So whose turn it is will be part of the state space, and you're going to have to incorporate that in carefully. Possible new runner locations. So possible new runner locations to me is like something that will be built into your queue function. I guess you could build it into your feature somehow. I'm not 100% sure how to make that into a feature. So remember, a feature is just, it inputs a state and outputs a number. Maybe something like the expected number your runners would advance, right? Which you can calculate like you did in Project 1 from some kind of combination of all the dice rolls. Runner positions, and so on. Okay. And okay, so to give you a little bit of a preview of next class. What did I do? I spent some time coding last night, and I made a really simple feature-based AI. So I made an AI that has some weights, and it combines them linearly. And this is the AI. It's based on this value function v, and the value function v, it divides the weights into 3 parts. So it has the runner weights, the location weights, and the number of columns claimed weights. So the features I use 3 types of features. What are the locations of the runners? There's 11 locations for the runners, so I have 11 weights for that is going to combine with that. There are 11 columns on the board. I turn that into 11 location features, and that's really the thing I ended up using was the difference between your opponent and you, right? How far ahead you are of your opponent. And the last one was the number of columns claimed. So if I've claimed 2 columns and you've only claimed 1 column, I should be winning. We're gonna have a weight for that too. So we're gonna go more into depth on this next time, and like kind of like it's gonna be like a guideline of how you can take what we've been doing and apply it to your final project, which you should start thinking about after today when project 2 is due. Let's see. What else? So I guess an important thing, if you haven't done it yet, your homework for tomorrow is to go to this site, rollardon't.com. If you haven't done this yet, you must go to this site and you must play some games of Can't Stop so you can learn what are the good strategies. So out here I'm picking 9 and 10, I pick 2 7s, I stop rolling, the computers go, it's my turn. And if you play this, you sort of will develop some intuition about the game, and that's important for putting into your features. So if you haven't done this yet, this is your chance now. Okay, I think I'm going to stop a few minutes early today. If you have questions about the project, please come ask them, and otherwise I'll see you guys on Friday.